对，站到这边。
哇。Okay. Yeah. So Anjin already graded your quiz. Okay, quiz 1, and the average is around 70 something. Okay. Yeah. So it's you have to know what's the problem. So I think before ending the second hour, Anjin will give back the quiz to you, and you will see it next week again. Okay. Yeah. Our midterm next Monday. Due to I'm going to German for the biotech, so our midterm will extend 1 week. Yeah. So if you have questions, please come to my office, and let's continue for the frequency spectrum. So our midterm will end up spatial domain, no frequency component. No worry about it, but you still have to be very careful to listen because our final will have this part. So in previous our introduction for the Fourier transform, so you have to know why we are going to change our signal, our image into frequency domain, because much easier to understand the component of your image and what you are going to do. So we said our Fourier transform is by definition, okay, for the remember that one, okay, we found Fourier series. And then Fourier series, your signal is repetitive. So in your frequency domain, you have a spectrum. You have a Fourier transform. After Fourier series transformation, your periodic signal, you will see the nice spectrum in your frequency domain. Okay, so it's like a nice spectrum, and it's repetitive. So very important idea is you have a repeat signal, and in your Fourier domain, it becomes nice spectrum. Because Fourier transform is a symmetric, okay, symmetric. So you can think about that one. If your signal sampled in your spatial domain, like a digital image, so you have a look like samplized signal in your image, and you will see their symmetric property. You will see it's a repeated periodic Fourier domain in frequency domain. Okay, your Fourier transform. So this is a symmetric property of the Fourier transform. Very important idea. And also, if your signal is become non-periodic, so what will happen? Every distance in frequency is your repeat frequency. So if you miss your periodic property in time domain, spatial domain, what does this happen? So when you extract it, increase your periodic space in time domain or spatial domain, the nice spectrum will become higher density, until it becomes continuous spectrum. So that's the general condition we see if you have this kind of one non-periodic signal in time domain or spatial domain. In your frequency, you will see it's continuous spectrum. Okay, so it's all fundamental conception of spatial domain, time domain, and Fourier domain. But for computer world, we have to do our image processing in which domain? In computer. So what can you do? You are going to sample in frequency domain. So it's a frequency domain. So you are going to sample it, become samplized. Okay. So that's what we say, discrete Fourier transform. So the final, from Fourier series, from continuous Fourier transform, and up to this discrete Fourier transform, and then samplized. It's continuous spectrum, and then samplized. So it's become endpoint discrete Fourier transform. So it's all Fourier transform conception. So So you can do it in spatial domain, time domain, discrete image, and you can do it in frequency domain, discrete Fourier spectrum. Okay, frequency spectrum. So it's an endpoint. So we have an endpoint in time domain, endpoint image in time domain, and endpoint in frequency domain. Okay, so it's a Fourier transform idea. So we have like what's the transformation like this one. So we have an endpoint. So endpoint image and Fourier transform. This discrete Fourier transform is like we write here. So it's a UV in frequency domain. So it's summation SY in time domain, SY in spatial domain, exponential minus J2 pi U X divided by M plus Vy divided by N. So that's your Mn image. And U belong to 0 to M minus 1. V belong to 0 to N minus 1. So you have an Mn image in spatial domain, discrete image. And also you have a Fourier transform. Digital frequency spectrum. So this is our story for the Fourier transform. So every image you can change to frequency domain and look at their frequency distribution. For example, like this one, is G of XY image discretized and then transform. Use this two-dimension DFT, and then Fourier transform to Fourier domain, and you will have Fourier transform of G of XY. It's become G of UV. Okay, so we can write is real part of the image and imagery part of the frequency image, frequency spectrum. Okay, so we have a real part of your frequency domain and imaginary part of your frequency domain component. And this one is look at the magnitude. So it's take the absolute value, so it becomes square plus I square. Okay, real part square plus imaginary part square. Take the square root, and also degree the phase spectrum. So we have two parts of the image. One is the magnitude. The other one is the phase spectrum. Okay, magnitude spectrum. And the phase spectrum. All important in your image processing. Okay, so the phase spectrum is just like this one. The image part divided by a real part. Take the arctangent. Okay, so every image, when you use some FFT, you can look at the magnitude spectrum. You can look at the phase spectrum. Okay, like this one. It's the cameraman's magnitude spectrum. This is the phase spectrum of the cameraman. If you change to another image, it's the other image is rice. Okay, so similar. Oh, we did it. Okay, so it's a magnitude and the phase of the rice image. So if you mix up, you didn't do it well. You didn't good naming behavior. So you change it, and if you take the cameraman, it's an image, the inverse Fourier transform. Okay, we can trace back to a spatial domain. But however, you use the magnitude spectrum of the rice, but mix up with the phase spectrum of the cameraman, and you will see this result. So just let you know, phase spectrum is very important. Okay, so and this one is the cameraman magnitude spectrum, but use rice phase spectrum to inverse process of your frequency spectrum back to real image, but unfortunately the image is screwed up. Okay, so here is an example to let you know how you calculate this one. It's a very small example in one dimension. So how you do it, and in MATLAB you just use FFT2 for 2 dimension for you. 1 dimension you use FFT command. Okay, so it's based on the definition for the one dimension is quite straightforward. So please make sure you understand how they process. Yeah, it's by definition for the endpoint DFT, and we use this one to calculate your frequency domain, magnitude, and the phase. Yeah, so just one by one. I'm not going to go to detail. Do it by yourself. You just do it by definition from n0 to n-1, and then your spatial domain data times this kernel, transformation kernel, and your endpoint will become 4 because you have 4 points here for this example. You have 4 points here, so n equal to 4, and then you can do it step by step and see the result. And you can see it's a real number, like your real image. Real image, okay, your image all real number, so it's a real image, no imaginary part. And however, change to the Fourier domain, it's become part of complex number there. Okay, so which means you have the phase angle. It's not all 0 degree. So the phase for the different content will have some phase angle occur. So they are corresponding. Like this one is a real number and imaginary complex number. So it has different angle. And also we can inverse transform and get back this exactly the same. Here, just try to remind you, when you do endpoint transformation, Fourier transform, you require the computational complexity of n squared, order of n squared. If you have an endpoint in your image, if you have an n, so you have n squared times n squared. You have to extend your image up to power of 2, and you can apply this element, but they will do it for you. Okay, just use FFT. They will extend it, by taking 0 of your image up to the power of 2. The dimension become power of 2. Okay, so they can apply some very fast algorithm. We call there are many different approach. And for the method, they use a radix 2. Radix to calculate to perform the Fourier transform, because some symmetric property of the Fourier transform. So it's very high efficient, high efficiency to perform Fourier transform. So the computational complexity will decrease to n log n, order of n log n. So it's from n squared down to decrease to n log n. So it becomes very efficient to do that one. Think about if you are going to do convolution in your space domain, it's also n squared. So you reverse and then multiply 1 by 1. So the power will be n squared as well. So I think FFT will become more efficient if you have a large image to process, big image to process, transform to frequency domain, and the process in the frequency domain will be faster than you do it in spatial domain convolution operations. So that's the advantage of FFT there. And later on we will see you have to do why you have to do zero padding, because there are some issue will occur. Okay, so 2D is just extended from 1D to 2D. So I think it's very easy to catch up. So it's become from MM to UV. So it's all the basic definition we just mentioned. Okay, so from MM to N, but some of them have this coefficient separate in time domain, spatial domain for easy calculation. But this is the basic definition for Fourier transform and endpoint, discrete Fourier transform, and inverse IDFT. Inverse discrete Fourier transform. So suppose that there is some coefficient in front of your inverse transformation on some normalized vector there, but you can separate if they have n equal to n, so you can do this one n1 divided by n1 divided by n, separate both time domain, spatial domain. But I think in MATLAB they use this definition to calculate. So sometimes you have to divide it back. Okay, this is for the normalization process. So FFT2 did it is use this definition. Okay, so never mind about the coefficient. will take care of you of that coefficient for you. Okay, just know how to use it. Okay, so I just mentioned sometimes they drop this coefficient in spatial domain, time domain, like this transformation power pair. Okay, so just let you know, and maybe you will say, oh, there's some definition error. No, both of them can be used for FFT and IFFT too. So for your inverse transform, you have to use IFFT too. Okay, so FFT2 will be the most important command for you to do this image processing in free domain. Okay, so here is some quick review for the property in your textbook. You can try to imagine every F1, F2 is two different images. How can you do that? And what's the property when you perform this FFT2 in your practice? Okay, so it's a linearity. Okay, so the Fourier transform have the linearity property. So you have two images added in spatial domain, and you can do that in breathing domain separately. Okay, you can transform first and then add it together. So their result will be the same. And this is the scale image. Okay, scale image. When you check your intensity level, okay, in your spatial domain, in your image in spatial domain, what happened? Okay, so it's all will be no, it's a time constant. It's not a scale in a coordinate. It's a time constant. When you multiply some intensity level in your spatial domain image, and actually it's linearity is magnified in frequency domain as well. Spatial scaling. Okay, so this is for continuous domain. If you scale in your spatial allocation, you are doing scaling. A may be some bigger than 1 or smaller than 1. Okay, you can think about that one. So you will jump your spatial coordinate to the other point. So A will be change your index in your spatial domain. B also in y direction in horizontal coordinate. What will happen? It will become like this. So it's some kind of scaling property of the Fourier transform. Yeah, so you multiply larger than 1, and in each Fourier domain will divide it by become smaller coordinate there. Okay, so it's a called scaling operation. So some sampling change, some sampling will have different representation in your spectrum. And also periodicity. So if we just mentioned the discrete Fourier transform is a periodic in spatial in frequency domain. So if you have this kind of operation, they will be the same. Okay, because it's periodic. So neither horizontal direction, vertical direction, that repeat by endpoint. So when you have this result, you are going to extract. When you use frequency domain operation, you are going to extract only n by n in your upper left corner. Okay, we will summarize all this process. So because they are repeat results, so you are going to extract only part of the output image from your processing. Okay, similarity. Okay, is the same. If you have some repeat n-periodic in m and n, so it's similar. Okay, separability of the Fourier transform for continuous discrete signal they can apply. Okay, what's that? Separability. Okay, you can see that our definition is like this one: fnm times the kernel exponential 2 pi blah blah blah, and it's for horizontal direction, vertical direction. However, we can apply it. So you can see you can do it in each row first. So when you're for 2-dimension image, you can do it Fourier transform in horizontal direction first, only in one direction, and then after that do it in vertical direction. So you can do it separately. Okay, we call it separability property of Fourier transform. Also, you can do it each column first. You can do the image transform each column by each column. It's a 1D Fourier transform, 1D DFT. and then after that you do horizontal again. So it can be do in two different ways, separately. Okay, and translation is an important property for this one. So sometimes you are going to shifting your image in spatial domain. Okay, like shifting right to M0 pixel and down to NO pixels. You are going to shift your image. And in print domain, actually the amplitude spectrum, magnitude spectrum, just keep the same because we know every magnitude value of this item will be 1. So the magnitude spectrum makes no difference at all when you shifting your image in spatial domain. But the phase angle changed. So later we have an example to show you. If you do some small location, okay, when you inverse back your original image, it will be totally different out of your expectation. Okay, so the angle is still important. The phase spectrum is important to be controlled, well controlled. So here, remember, if you shifting your image in spatial domain, in frequency domain, the magnitude the same, but the phase spectrum will be changed. Okay, so this is the idea. And conjugate is if MN is real image, we always process our image as a real image. Okay, and FUV, after your phase Fourier transform, discrete Fourier transform, is a conjugate, symmetric. What's your conjugate? Conjugate is defined as if your image is imaginary location, real part, image part. So it's if you change this one to this one, you will see a conjugate. They are complex conjugate. So which means the magnitude spectrum, magnitude is the same, but angle exactly reverse, 180 degree. Okay, so it's just use this conjugate symmetry. So how can we do? We usually apply this one. Okay, that's what we mean. Because we want to shift our frequency spectrum in the center. You will see low frequency component at the center. So you want to look at your magnitude spectrum. It's center here. Okay, low frequency part in the center. However, at the beginning, when you transform to frequency spectrum, your low frequency will located on the corner, 4 corners. So how can you see that one? Because we told you it's with periodic spectrum. So you will see the low amplitude here. So you are going to look at here. So that's our conventional way to look at your spectrum. Low frequency component located at the center of your magnitude spectrum. So how you do that one? So you have to do some shifting process here. Also, instead of this FUV, we always display our image magnitude spectrum in U divided by minus n point divided by 2, and the V minus n point divided by 2, because your image is n by n image. So you are shifting to center here, since it is easier to visualize the symmetry of the spectrum, okay, of your image. This is done by this using FFT shift. Okay, we just mentioned how you do that one. So FFT shift is just use your plus minus 1 power to xy, your index coordinate in spatial domain. How you do that one? Because I will switch it. If your x is even number, it becomes positive 1. If your x is the odd number, it becomes minus 1. So your image becomes positive, negative, alternative before you do some Fourier transform. Okay, so that's the way you can switch this one to the center. So that's a constant. You are going to use that one, fine. But your result, if you look at your magnitude spectrum immediately, you will see your low frequency component will locate it at the corner. It's not a good one. So how do? You are going to multiply this one before you do FFT2. As a custom, you use MATLAB, so you'll do it in your next homework, okay, after the midterm. And you are going to alternatively switch your image in spatial domain by this coefficient here, -1 power to the x plus y, the coordinate, the coordinate of your pixel location. And in this way, and they are going to shift there. And why? You can imagine, like this one, so here, see, how can we do that one? Here, -1, there. So they just change to here. If you have the shifting property, okay, we can see the data. Okay, we'll demonstrate. I think the textbook will say that one. Okay, see, this one is the example. If your image is like this one, and you're going to look at your final spectrum like this, the low frequency component located at the center of your frequency magnitude spectrum. How can you do? How can you do? It is you didn't do anything. You will see this result. You are going to use FFT2 and then look at the result. You will see low frequency component located at the corner. Okay, but it cannot imagine what's the magnitude spectrum distributed in your image. So if you multiply before you FFT2 to this one, you are going to multiply this coefficient before you apply FFT2. In this result, you will see your magnetic spectrum will be shifting. Okay, will be shifting to the center of this one. So it's become more understandable of your magnitude spectrum distribution. And you see, low frequency have the whiter intensity represent higher magnitude spectrum, more power distributed in low frequency component. So that's a way we want to look at it. Okay, so it should be better than the other one. Okay, so how you do that one? Remember, before you apply FFT2, you are going to multiply the -1 to the power of n plus n there. And in MATLAB, they already write this for you. We call FFT shift. FFT shift. Okay, if you apply your image here, FFT shift, and then before FFT2 transform. FFT shift is do that one. Multiply this easy. You can write it by yourself, but you can apply that one. I think there's no tool there, shift to, yeah. FFT2, they'll do it automatically, depending on what's the dimension of your signal. One dimensional also use FFT2, FFT shift, and two dimensional also use FFT shift. Also three dimensional, they can detect your input signal. And always in MATLAB, we use FFT shift first, and then FFT2 of your image to get the result. Okay. Yeah, and then you can see the amplitude. I remember I already showed that one, right? The code. Oh yeah, here. See? So that's the way we do that one. If you have an image there, this is try to create a circle image. Okay, so if you have an image, you just FFT2 and then FFT shift. And this one is your Fourier transform result. And you are going to look at it. However, if you can imagine, the magnitude of your frequency domain is from a small to very huge number there. So if you just immediately to look at it, image, to look at a figure, you will see see nothing because you cannot compare. So we always apply log magnitude to make the data become comparable, okay, visible. And you see the magnitude spectrum, we use absolute value, ABS, and why +1? Because sometimes it will be 0 at some location of your frequency component. However, you don't want to lose it, becomes some error there. So you +1, try to solve this dilemma, and you take a log and then take the magnitude, and you will see it. Okay. So this is the way you look at your image, and this is try to normalize. Okay. Find out the maximum number and then try to normalize. Okay, and see this one. For example, like this one, and we know it's a circle image, and after you apply FFT shift, and then do that one, and you will see the result will be located in the center. Okay, so it can be expect this result for the circle image. Okay, you should understand what's the mapping result, because in every different direction they are also should be a sync function. Every profile is just, if you look at every profile, it should be a rectangle shape in every direction. Okay, in every direction, and so in every direction is all like a rectangle. So you will transform to a Fourier domain, it becomes sync in every direction. So if you have every direction has a sync, it becomes like a ring image in magnitude spectrum. Okay, so that's the way we do our Fourier transform in image processing. Okay, FT shift to there. Also, the next one important property is convolution. Oh, convolution is what we did our filter design in frequency domain. Okay, so convolution is spatial domain operator. You remember? You fix one without moving, and the other one is okay. I use this example. Maybe like this one. Okay. So how you do it in spatial domain? You fix one signal and the other one flip, and then move from negative infinity step by step to positive infinity, and then multiply. So this one will be a change in frequency domain. They will become like this one, and then moving step by step. Okay, and then go to here and then calculate the overlapping area step by step, and you will get a result. However, in frequency domain, you transform into frequency component, and F is FUV, H is HUV, and you see the operation become multiplication. So it's become very easy to understand what's the result you can expect. Okay, so it's convolution. You cannot imagine what's the result. Okay, for example, you know the rectangle convolve rectangle in time domain. What's the result? It's become a triangle. But if we look at it in Fourier domain, it's much easier. Okay, this one you just use multiplication. So we look at this this spectrum here, and then we know what's our design in filter. Okay, maybe you design some low pass filter. You hope you have an ideal low pass filter in frequency domain. Okay, UV. Okay, so you can see if I have this image only low pass filter, only this part I'm going to remain. All higher component, free component, I'm going to remove. So which means I'm going to take this left, discarded orders from the outside the rectangular box. Okay. So it's frequency design, low pass filter. And this filter is ideal low pass filter. Very good one in spatial domain. We will see the problem of this so-called ideal low pass filter. What's the result will occur. And you just take off this part and discarded all the surrounding area. Multiply, because you multiply this one. It's a constant one here and 0 outside. So only this step. So, and which means you are going to apply a low pass filter, right? very easy, very straightforward, intuitively. Intuitively, you can see only low component will be remain, high part will be discarded. So it's a called low pass filter. If you want a high pass filter, how do you design? You can design an image and then discard it, only this one left, and multiply to this one, and the result will be only high frequency component will be remain. All the low frequency component will be discarded. So what will the result? So if you know the image, all the edge information is in the high frequency component, and you'll see there's a edge detection, like edge detection. And this one, if you only keep the low frequency component left in your frequency magnetic spectrum, what does it mean? You are going to apply some low pass filter, smoothing filter, because you discarded all the edge information. All the edge information in high frequency components. So you discarded all the edge information. So what will result? It will become smoothing effect. Okay, like your photo image, your personal head photo image, you need low pass filter. Okay, otherwise you don't want to highlight your pimple on your face. Okay, right? So this is applied for some smoothing effect, and this is for some enhanced edge detection. Okay, so it's much easier to explain what's your filter look like. If you only have to use multiplication operation in frequency domain. So it is important to understand. If we change to frequency domain, the convolution is just like this. Okay, convolution in high domain, in spatial domain, is a very complicated operation there. But in frequency domain, you just use multiplication instead of convolution. Okay, it can be demonstrated. I think at the beginning I already showed that one. Also, this one is different approach. We call you multiply the this is the output of linear transformation, linear transformation of this point square function. Okay, what's the point square function? What's the point square function? Point square function, PSF, is called point square. Function. Point square function is just delta, okay, delta signal. Okay, in one dimension, and for the xy, point square function is delta xy. It's located at the 0, xy located at 0 here. And you can shift it to any location. So it's a delta x minus x1, y minus y1. So it's shifting depending on the location you are doing. So what's the Fourier transform of delta, the point square function? It's become a constant one. A constant. I always showed that before. So if we want to look at what's your system filter design. So I have a system here, H system. Actually, H of XY. Okay, I have a system design. I don't know what's this low pass filter, high pass filter. A lot of IC circuit design there, and I'm going to put my image here, and I don't know what will be the result. How can you evaluate what's the system? The easiest way is give the point square function as the input here. For the space signal, you use delta t. For the image signal, you use point square function is a point start, only one start, 1 to 55 intensity in the center, O0 outside. Put into the system there. That's the system scan your image or this point square image, or use the tape signal to receive your impulse signal. And what's the result outside? It's you can see any signal f of in time domain. Okay, confused. F of delta t convert x of t is become x of t itself. Why? Because we say the Fourier transform of this one convolution become the delta constant multiplied x omega. Okay, so everything becomes itself. And if you take the inverse of this one, you get this original signal back. So now we have this one, and if you put it inside of this to your filter h omega there, or h of t here, your impulse, your filter, and then the result will be h omega. Okay, and the h omega inverse become h omega inverse become h of t. So you know what's the design here. What's your constant there? What's your filter there? Okay, because we times constant one. Impulse, the point spread function here mentioned. You can put your point spread as an image, input image, and you can see what's the filter design there. Okay, so because the commutable, you can also if this is a delta here, so everything signal there, output will be itself the same. Signal come up with a delta or become itself, or everything come up with delta, it becomes itself. So it depends on your application. But here just tell you, the point spread function is quite powerful to test. Okay, test your system and see what's the result. And here just give you some idea. The filter, the point spread function can be used as a system. And this correlation, because of correlation, right? Now let's see the correlation. The other one is called correlation operation. So in image processing, we also use a lot of correlation application there. What's the correlation? So correlation is defined as like this one. It's not solid circle. It's empty circle in our traditional way to represent correlation. And that definition is different from a convolution. Okay, it's like this. The fundamental definition for the correlation is you have f correlated with h. What do? You just fix f, and then the h is moving in the right direction everywhere, and then multiply with your signal, and then do some integration or summation operation there. So you can imagine, if I have an image here, or some textbook, and if I have another small image, I'm going to find out, do you have this sub-image in your original image here? What can we do? In this application, you are going to make some exactly the same or similar sub-image, and you are not going to do convolution. You apply correlation to finish this task. How can you do? You just do this sorry, it should be an empty circle. Okay, so I'm going to apply correlation, and you can see this small image will go through from this original image step by step and matching, multiply, summation, multiply, summation, multiply at each pixel image, and then sum up as a result. So you can imagine this small image, when they go through all this location here, where is the highest value you can match? Only in this location, the t will mapping with the t exactly at the location, and you'll get. It's always applied in template matching. Try to figure out where is the highest similarity of the two components. Okay, so this definition you can imagine, and actually you can change it to convolution, but the result will be totally different. Okay, so if you change correlation to convolution, let's work like this one. Because correlation didn't flip-flop your image, they just go directly. Okay, they didn't flip-flop left to right, up to down. No. So if you want to use convolution to represent your correlation operation, you have to flip-flop first, and then get some conjugate later. So it will be the same result. Okay, so correlation and convolution still have some similarity, but the principle is one fix the kernel, didn't do free flow. The other one is they have some conjugate relation result there. So here is just tell you, if you are going to do some correlation there, and actually you can apply convolution, but what do? You have to do this pre-processing of your image, and the result will be the same correlation. Okay, so it's just like the multiplication in free domain. Your kernel and your image have to be conjugate, so the result totally different. So correlation and the convolution have some different process. So make sure you don't mix up. And then if you do FF itself, what's that? F correlated with F. So we call it auto correlation of the image with itself. Okay, and from this auto correlation result, you can see what's the highest value is located at where, should be the same. Okay, exactly. And the cross correlation is applied on two different signals, F and H. And this is what I say. You are going to temperature see where is the most similar component of these two images. Okay, so it's auto correlation, cross correlation operation, and roughly speaking, FH cross correlation measure the degree of similarity. So different application from our convolution. Okay, and large value of this one would indicate that image are very similar. So we can compare two different F and H. Are they similar, or F and another H1? Which one is similar? You can do this one and compare their result. Larger value represent more similar, and usually like a temperature just mentioned, or you can have this idea. You have a sub-image correlated with a whole image and see where is the largest number of the correlation result, and that's the location. You match the sub-image in your original image. So also this the comparison of two images, you can use the one. Okay, so okay, we will see. You are going to do some zero padding before your operation. Why did that happen? Because if you don't do that, you will sacrifice the boundary condition. Because we mentioned the zero padding is try to make sure you don't have the overlapping, what we call left around arrow. Left around arrow here. Some arrow message, because you didn't padding your image to a right size. Unfortunately, some error will occur in your boundary. We call it a red around arrow. So our image always will do that one, because you know you are going to perform F convolve H to get the result you want to do. Maybe low pace, high pace. Unfortunately, this is the size of MN. This is the size of KL. Okay, they have different size. So before your processing, you are going to do some of the result, and you better because you are going to use in frequency domain, and you make sure you have already padding 0 for m plus k minus 1 times n minus L plus 1. All these images, these two images extended and padding 0 outside. Otherwise, we have looking around arrow. We will see it later in a slide in our textbook. Okay, I'll take 10 minutes rest.你这时候我需要看吗？你好，这个我看没有用，他们看，因为答案我已经给你了，对不对？那你会给他们答案吗？有，我已经传了。哦，已经传了，是？那很好啊，那很好，那就对啊，那就看到那看他们要来拿。
就是当一个 high boost 的作业，
对，
用课本的形式。
可以啊，可以啊。
因为
这个其实都是其中一种，对，那个也是比较直接了，比较直接了。
所以这个我有个疑问，它是把那个权重放在原图上。
对。
可是你权重放在原图上面，不是会把就是high boost 就这个 high boost 的效果减？
看大小，因为有时候你原图的重要性这很难。就是说那个影像的边界也不见得像你想象的就很分明，有时候要强调那个影像的边界，那看原来影像如果很大，你弄起来很自然。
所以就是看需求，然后
对，那可以调的，都可以调啊，对，都可以调，都可以调，对啊，这个一样，这个东西只是在 Mask 上面做一个，对，
它这个应该是主要是强化
边缘，对，High Boost 的 High Frequency 的 Boost， 把它给启动它高频的地方，好，试试看嘛，应该都可以，这个还在定义啦，
周宇轩，陈思杰，焦宏源，严瑞宽，周梦杰，王家辉，吴彦志，张维恩，卢义宏，安国光，陈维军，黄兴哲，宋典燕，朱国轩，邓基成，方宇杰，陈柏勋，康一彤，陈少彤，郭正阳，肖家福，许家瑞，吴瑞成，魏世涵，陈宏伟吧，错一的，薛玉哲，陈明耀，曾祥宇，周子瑜，刘品平，潘玉霞，赖进兴。 黄宣和、李宣文、卓雅璇、那个我已经把答案放在上面了。I have upload solution on my score。所以如果有问题的话，可以照这个看，然后有改错的再跟我讲。那个学校要求我要给你们填这个问卷，所以如果大家有方便的话，帮我填一下。好，没关系。 I have created a Teams group. So if you have any question about homework or quiz, you can consult online.
Okay, so yeah, if you want to do it in your frequency domain, and you have to padding zero before you doing FFT2. Okay, we call it zero padding. Okay, zero padding of the image. How you do that one? We just mentioned your image size and your filtering size. Filter size. You are going to extend it to like this one. We will show it later. So we need to have this to be a size of this one, and therefore you should want your, because of the periodic property of your Fourier transform. So you want to make sure there are no overlapping error occur in your during your process in Fourier domain. So we call our F will extend it to this image, and we call it extended zero padding image on your outside. Actually, you can do different padding process and see what's the result. Okay, so H is your original mask. You are going to extend your image to the size of the same. Okay, the size will be the same. And then after that, you apply FFE2, and you do that one. So now you can multiply in your Fourier domain image directly, because you already extended. You can multiply together and then inverse transform to get your result. So that's the process, and we'll see what's going to happen if you didn't do it well later by example. And multiplication, okay. So because of the symmetric property of in time domain, spatial domain, and the Fourier domain, so you multiply in a spatial domain or time domain. Actually, it's a result in a convolution, a relationship in a Fourier domain. So if you do multiplication like your sampling process, okay, the H is the sampling function. Actually, you are multiplying. So the result will be convolution. Okay, so you can easily imagine it. If you have some sampling function there, and sampling function is depend on the delta t, what's the sampling time, right? If your sampling time is too large, and what happened? The infinite domain, you will become delta t 1 divided because of frequency, right? We will sampling has a minimum sampling requirement. What's the minimum requirement? It should be double of your frequency band of your signal. Otherwise, your signal will overlap. What does that happen? Because your delta t in time domain here, the sampling file here, the delta t is the distance in your time domain. And in Fourier domain, it becomes frequency. So it's a 1 over delta t. So it's 1 over delta t there. So if your delta t is too big, which means your 1 over delta t is become too small, and it becomes very small. So the first periodic will like this one. Okay, if your delta t is not small enough, the frequency component will overlap. So if delta t is too big, what happens? The delta t will 1 over delta t will be small, and there will be some overlapping. So this is the idea. You will see the sampling rate should be very high enough. Delta t should be very small, and in that sense, in your frequency periodic signal will be not overlap, and you will not lose your signal. So also the same. We are talking about two images there. So that only process. So the same. If you don't have enough padding zero area, your image will have some a problem, the wrapping around error occurred. Okay, so let's see. Difference is like this one. So it's the multiplication. Okay, is just tell you the relationship in time domain, spatial domain multiply, and in free domain it become convolution. How about differentiation? The property of the differentiation. So if you take the derivative, so what do you do in a time domain, spatial domain? Perform the derivative operation, which means you want to look at the differences. And if you do that one, actually in spatial, in free domain, and take Fourier transform of the derivative operation, and the result will be exactly the same, just only have some coefficient occur, minus say 2 pi u, okay, and which means the magnitude of this one, they have some try to emphasize the age component to look at it. Okay, so this is if you look at the mathematics, they have some different. Here is just tell you we have some Laplacian operator we performed before, and this is second order derivative on this one. And it become what? Become your magnitude spectrum will multiply this one because it's double it twice, so you are going to have the square of this coefficient. So you have this magnitude in your horizontal line in large, and then in horizontal vertical direction you have this one. So Fourier transform of this one. Sorry, this needs some Fourier transform operation, and you get this result. So it's for derivative operation, and it's just like your frequency spectrum multiply some different coefficient there to amplify. So here is the Fourier transform for what? Yeah, centering. This is just what we mentioned. If you want to look at your image in this center, because of your transformation, UV access here. So your result like this one, and you look at your image is not locally component in the center. So you are going to shift into -1, -2, and here. So I remember this should be some equation. If you multiply this one, it becomes -1. I think yeah, okay, so never mind, just the result, you know the result. You just multiply this one in your time domain, spatial domain, for the x direction and y direction. So -1 to y squared, y power, and you will have this shifting result. Okay, so the textbook summarize all the property of Fourier transform and some example how you do that one. So let's double check the result here. So if you have an image like this one, and B is the spectrum showing the small, so you just take a Fourier transform, FFT2, and you'll see nothing. Actually, should be at corner. Okay, so that's we said in the UV coordinate. If you didn't do anything, it's not clear. But if you multiply -1 plus 2x plus y, and the C result is central spectrum. So you can see the corresponding exactly the same. Just you shifting to the center, you are going to look at it. And D is the result after log transform. So I just mentioned because the magnitude of in a spectrum is a large range, dynamic range there. So you are going to look at it clearly. Please remember to take a log 1 plus FUV. Okay, that's the way we do. Okay, 1 is just protect log 0 occur, and you will see that should be like this. Very clear. You can see original image, the rectangle bar, and its corresponding Fourier spectrum, magnitude spectrum is like this. Okay, much clearer. But if you don't know, it's just you told me just use FFT2. I can see the result, right? But unfortunately, you didn't do the right way. Okay, so try to multiply this first, and then take log next, and then you will see the magnitude spectrum clearly here. And you have to expect the result. You understand because it's long in vertical and narrow in horizontal. and the result should be like this. Why? Because we know it's your in one dimension. This is wider. You get a sinc function magnitude. Okay, if you have a wider, and what do you get? You have a narrower, right? So it's the basic concept of the Fourier transform. You're wider in time domain. In the frequency domain is narrower. Okay, so in this sense, you have a long shaped rectangle. So in U direction, you will have a bigger sinc function. So here is a bigger sinc function, wider. But for the vertical is wider, right? So in vertical, it becomes narrower. Okay, so in that sense, the rectangular also get this shape. And if you magnify, you will see this result. Okay, how about this one? The shift in spatial domain, in time domain, shifting, like your voice, just 5 seconds later, and then to Fourier transform. An image shifting to different locations. What's the result? If you look at the property there, and you will see actually it's just some phase angle change in frequency domain. But the magnitude, because you tie some minus exponential when you are shifting. So if you look at the property there, you are going to time the exponential some turn there, depending on your shifting. Okay, some there, and you have your FUV here. So it's you how many position you shift there. So some component there, and this one take a magnitude, it become 1. There's no effect at all. So you can expect this image and this image, they have exactly the same magnitude spectrum. So you can see the magnitude spectrum is exactly the same. Will not affect only some phase spectrum. The phase spectrum we will see later and will be changed. How about this one? This one is exactly the same, the rectangle but located in 45 degrees. So you expect the result will be like this one. Okay, the degree change and the magnitude spectrum the same. So you take the profile, take profile here. It's become a small rectangle. Take profile, it's a wider exponential. So it's just like this one. This one is a narrower spectrum, and this is wider sinc, and this is a narrow sinc here. Okay, so you are going to make a decision. If I give you a test on how you matching the original image and the result, you have to understand. How about this? This is a phase angle image of the center we just mentioned. The center, translated, and located. So we have 3 images here. The original image located in the center. The second is shifting image, not in the center. The other one is located in 45 degrees. Their spectrum like this. So in the center and shifting, you can see when you shift the image in a different location, but the phase spectrum exactly different, totally different from the previous one. Although they have an identical image in the content, but you are shifting. But when you multiply some the component there, I'm sorry, the result will be totally different in phase spectrum. And the magnitude spectrum exactly the same, right? The that one and the top one and exactly the same. They have the same magnitude spectrum, but the phase totally different. And for the rotated one also, they become like this one, and not exactly like original one rotate. So it's the phase spectrum of this corresponding image there. So make sure you know the right phase spectrum there. So this is the real image to look at it. This is the Boy image, and the B is the phase angle. So B is the phase spectrum. And now we use Boy image, reconstruct it using only its phase angle. But now we are going to discard the magnitude spectrum. What happened? We are going to discard the magnitude spectrum. So there's no magnitude, only phase spectrum. Also, you can inverse Fourier transform. of this one. Okay, of F image, FUV. Okay, how you do that? You can use IFFT2. Okay, so IFFT2, put that inside your R plus JI there. Okay, so you can reverse back your image, but if you discarded this one, I only have the face left. And what the result? Just like this. You still can see something there, but unfortunately, the magnitude all disappeared. What does that mean? So the magnitude is represent some intensity label there, right? We just mentioned you have a low pass filter. If you take away the low pass, the energy of the image, the most energy part is in the low frequency part. It's represent like the DC value. It's the average intensity level of the image. What's the F00? FU transform to FUV. Okay, and F00, the local, the zero in frequency domain is a DC value. What's the DC value? It is the average of this f of xy divided by n. And so the DC value is average value of your image. And you can see the low frequency component of your image contain a lot of intensity information in your image. So if you discarded it, you will see no intensity label there. Only partial edge information you can observe if you discarded all the magnitude spectrum. But there are still some edge information occur. Okay, so how about this D image? The D image is the void image reconstructed using only its spectrum. Okay, if you just throw away the phase spectrum and only have my magnitude spectrum to do inverse transform, IFFT2, what's the result? Nothing left. You can see nothing because all the edge information disappeared, right? So it's only the low frequency component so it's nothing you can observe. And if void image, the E image is void image reconstructed using its phase angle and spectrum of rectangle. Okay, so if we use this magnitude spectrum here, this one is a magnitude spectrum plus the phase spectrum of this one. This phase spectrum. Okay, see nothing there, but it's a phase information of the image. You combine the magnitude spectrum of the rectangle and phase spectrum of the void. What's the result? Like this. Smear out, but still some shape of the void. Okay, because of the phase spectrum. But unfortunately, most of the detail disappear. How about the D? F image is a rectangular image reconstructed using its phase, rectangular phase, and the spectrum of the void. So we use a void magnitude spectrum. It's including a lot of intensity level information there, and the phase spectrum of the rectangular become like this. So you only can see the phase shape, not phase shape, the rectangular shape of this image, because we told you the phase spectrum still contain a lot of agent information there, and so don't make the wrong combination when you're doing IFFT2. The phase cannot be discarded. So most of the time, we only process on magnitude spectrum. We'll maintain the edge information, the phase spectrum there. We don't do multiplication because it's very dangerous. You screw up everything there. So just process on your magnitude spectrum during your operation there. So this is the idea for that current is just let you know. Okay, if you don't pay in zero enough, what will happen? What will happen? Actually, it is a better idea if you use the same width of the rectangle. Okay, because it just let you know in time domain. Okay, do some convolution. Okay, it's a time domain MN here. So what's that? That current spatial convolution computed using the approach described in this one. right current is circular convolution. Actually, it just lets you know if you're heading the zero, there was some wrap up rounding error there. Okay, so better make sure there's no overlapping of your in frequency domain. So the better way is you have to add up your original F and H. Okay, in some F and H. Like this one is a 300 and this is a 200. So if I'm going to do this one, and especially I'm going to in the frequency domain, so the better one is 500 point, it will be good one to do. So if you extended this to 500, there are some zero there, and also this extend to 500, so there are zero there. So in that sense, you do convolution, you do the Fourier transform after multiplication is also same for you. So we can see the result. Maybe there's some example. Okay, should be in the second one. Okay, let's see. Okay, chapter this one. Okay, so they have textbook provides you a real example. If you do some try to avoid the wrapping error, how can you do? It's just the only way you can do is head in zero before you do the filtering processing. Okay, so let's see. Let's use some example here. So this is a SEM image, and this is a damage the integrated circuit there. So not only the rectangular image or circle image, you have to know the corresponding Fourier spectrum. Even in the real image, you can expect what's the difference between the two images. For this example here, actually there are a lot of rotated rectangular and the white bar there. So you can expect what kind of magnetic spectrum of this image. So we just mentioned this image will have a lot of rectangular bar there. For example, like this one, there's a white stripe. So I can imagine there should be some spectrum in this degree, vertical degree. Okay, in this way, some energy distributed in this vertical angle there for this image, and a lot of this one. So there should be a lot of magnetic spectrum occur. So see, so that's the result for this image, the magnetic spectrum. Okay, different from the void. And this is the corresponding Fourier spectrum of A, and the magnetic spectrum, you take a log of the FFT2. Okay, so the result filtering the image in this with a filter transfer function, let's set 0 to DC current. So what do you do? So if this is the transformed image, and I take away this DC value here, the DC value is f of 0, 0 here. We just mentioned, when you look at the f00, you are looking at the DC value of this image. The intensity level add up together divided by the size of the image. So you represent the f00 here. So if I'm going to take away this one, so what's the result? Only take one point out, the 0, the DC value. So the result will look like this. It's the same of the original image, but however, every pixel will be minus the average of fxy. So if you remove the DC value point 0, 0 there, what's the result will be? Exactly the same this image, and then you multiply the sum of all the pixel value and divide by the size of the image. That's an average DC value, and every pixel minus this DC value. The result will be like this one. Okay, so that's the same way. If you transform to frequency domain, but I only use the point square function is only one point will be removed. DC value will be removed. What's the result? The result just like this one. So you can compare the original image and this one. This one is no average value, no DC value there. The DC of this one becomes 1. Of this new image becomes 0. Because every point is a minus. Okay, so the DC term is removed. Okay, so the result like this one. So now we are going to design all these different filter, and it become more clear how we do that one. So again, if we want to look at this image here, how do you do? I just keep reminding you, you have to have FT shift first. Use this one. Remember to do that one, and you will see this one. Okay. And in spatial domain, you do this one, but in frequency domain, you do this one. FFT2 of F image. Okay, this one you can see the one. Otherwise, in your spatial domain, you have to do this before you go into Fourier transform. If you do this one, you don't have to do FFT shift. Okay. So let's look at this the image here. This is immediately, if you look at this HUV, it's a free domain, HSUV. So what does that mean? It looks like Gaussian function immediately, right? It's a smoothing curve, like a Gaussian shape. Nice. See, UV here. So the center is 1/2 by 2n, one half of m. So it immediately you can see, okay, so this is the low-pass filtering, and located at the center of the frequency domain, and it's HUV. And this one, what's that? It's also Gaussian, but upside down the Gaussian. So how do you do that? Easy. 1 minus low-pass filter. So if this is H, this is 1 minus H low. You can get this one, right? It's upside down. Use a constant to minus your low-pass filter, and you get this one. So what's that? It's a high-pass filter. So you can see at the center, will be removed, and the higher frequency part will be maintained. And the next one is what? The next one is offset high-pass filter. So we call this offset high-pass filter. C is a low-pass filter, high-pass filter. C is the offset high-pass filter. What's that different? Do you see that one? You still maintain a little bit the DC value. The local frequency is not zero. If you remove this one, you can see exactly the DC value disappear because it becomes zero. But here, we still maintain some value at the DC level. It's A intensity for the DC value. So it's just a little bit different. So what's the result? You can see. If you apply this one in your image, original image, can you expect what the result will be? Okay, so it's a low-pass filter, right? Low-pass filter, which means I'm going to smearing the image, smooth the image. And the original one will become like this. Immediately, the image will become smooth, smeared. Okay, how about the high pass? High pass is for the edge information. So the edge clear, but the low frequency component disappear. How about this one? This one is a high pass filter, but partially low frequency components remain offset because offset high pass filter. Okay, so this one you can see the low frequency component still maintained, but the high frequency component is enhanced. So you can see it's very clear for the detail. And the color is not like this no DC value. Okay, similar to original one, but this one is for smoothing. So it's very easy to see this one. Yeah, so if we write one, you are going to do it in spatial domain. Just remember the process. We'll summarize in end before the class end. So you pre-processing. If we do it in your space domain, try to multiply -1 power of xy of -1, and Fourier transform FFT2, and then multiply your filter, this filter design, and then inverse, and then after that you have to come back to remember. Okay, so actually remember this one, and then to DFT, right? FFT2, and then use your filter design, right? Low pass filter, high pass filter. And then after that, you want to look at the result. You are going to use IDFT, right? Inverse Fourier transform, IFFT2, right? This is FFT2, right? And this one is FFT2 shift, okay? And get this one. What's the result? If you inverse, can you expect, is this the origin? Is some f of xy, multiply this one, and then get this result? Do you think it's exactly the same what you expect? The answer is no. Because remember, we have to do some pre-processing here. What do? You alternatively times -1 at your image. So when you get back this image, you have to multiply again back. So some students always forget this process. Remember to multiply this again, FFT shift. So in MATLAB, I think the program is called IFFT shift. Okay, so if you use a FFT shift here, to do it, remember here you need the IFFT shift to make it back. Or you are going to multiply -1 to x plus y. The coefficient alternatively change it back, and you will get this result, your expected result. Okay, so this result is not directly show as you see. Oh, I'm going to do that one and do that one and do it in frequency component and apply to the low pass filter. But the process you have to pre-process, multiply this one, and then FFT2, and then design your filter, and then multiply to this filter in frequency domain, and then inverse Fourier transform back to spatial domain, and again multiply -1 to x plus y power. This inverse Fourier transform shifting process, and then you'll get your image result like this. Every step you miss, you cannot expect what you see. Okay, so let's just remind you there. This one is an example of the padding 0. Okay, so you can see this is an original simple image here, right? Original image. This is the result of blurring a Gaussian low pass filter without padding. Okay, you can do whatever. Okay, you are going not to consider your low pass filter in size. You just use original n by n, and your filter is some forgot what's the parameter I use. Anyway, so KL. So if you didn't do 0 padding, this will be the result. You still can see some of that, some the boundary information because it's blurring, right? It is use blurring with a Gaussian low pass filter. This filter, Gaussian low pass filter. What's the result? Like this. So some of the boundary is fine, but some of boundary they didn't do anything. So you can see that all the boundary should be smooth. But if you do 0 padding, low pass filter with 0 padding before you process, it will become like this one. So every edge in your original image will be done, will be smooth. So you can see the difference, especially for the different location. So it's just let you know, if you want to have the positive every boundary is effect by your filter. So you have to do this 0 padding. So m plus k -1, n plus l -1. If your size is m by n and filter is k by l, so you are going to extend the other one, they'll be fine. And this is also just like the idea, the previous one. So this is the image there. If you padding 0, okay, you padding 0 like this one. Sorry, should be this one here. Actually, it's a lot of periodic idea there. If you didn't do it, so the periodic there and the low pass filter will do something there. So you can see there will be no smoothing effect on this location. That's the reason we see there's no smoothing effect there, right? There's no edge. If you didn't padding 0, they'll repeat like this one. So in the horizontal direction, it's continuous, white color. But if you do the padding 0, what's that? You can see the boundary here, 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 here. So as a result, you can see here also smooth, right? Can you explain that? That's because you do 0 padding. You do 0 padding. So they look at your image like this one. You padding the 0 on your boundary, and your filter apply on this one. There's become an edge, real edge in every direction, every location of your original image. But if you didn't pad, it still repeats signal layer, but they repeat here. There's no edge occur in this horizontal way, right? So that's the reason why there's no effect for smoothing for the edge. The high frequency component maintain the same because there's no edge. Because the periodic tell me there's no edge there. So unfortunately, your low pass filtering doesn't cause any effect on this boundary. However, if you repeat padding 0 before repeating periodic signal, and the edge occur here, right? That's the reason. Okay, because you padding 0, padding 0, padding 0, padding 0. So there indeed an edge in original one, and the result will like this. Okay, let's just let you know. But otherwise, if you read in the textbook, it just tell you they are different. But how can you explain? If you pay 0, there's some smoothing effect on the vertical edge. Why? That's what you do, low pass filtering. And what you have done, 0 padding, and the edge will be smooth. Low pass filter for the smoothing effect. Not smoothing or smear effect. Smearing effect there. Okay, so that's the reason. Now you understand. 0 padding will have this result. But let's look at this one. What's the true effect if you use so-called low pass ideal low pass filter? So let's see this one. This is a filter transfer function specified in the center frequency component. Okay, we imagine you use the profile to look at it. Okay, so it's a 2D, and you use a profile, and you will see this one in U direction. This is a filter transfer function specified in a frequency domain. So it's a frequency domain here. So remember, you have to understand the image you are looking at, the signal you are looking at is in spatial domain or frequency domain. So now we are looking at in frequency domain. So what's that? It's just like an ideal low pass filter, right? Clear cut at different location, clear cut. So it's a low pass filter. If you look at this image, it's a low pass filter. If I magnify this one, low pass ideal up to the other point, 0. Between the center point, there's pass value 1. Okay, so it's ideal low pass filter. We say it's an ideal low pass filter. So can you tell me what's the inverse transform IDFT of this signal? So if you have a strong frequency signal processing background, you know the tangular function inverse transform back will become a sinc function. So it's a sinc function, right? Sinc sine x divided by x, sine t divided by t. Okay, it's a sinc function. We call it sinc of t. It's sine t divided by t. Okay, so at the 0 point, it's become highest value, and become the sinusoid function when time is increasing, when x is increasing, the denominator becomes larger, so the size becomes small. The sinusoid becomes smaller until to 0. And we know it's because it's a discrete Fourier transform. So inverse is all repeat signal layer. So in time domain, spatial domain, also only this point left, endpoint. Transfer back to the also endpoint there. Okay, this digital signal endpoint there. In spatial domain, in free domain, they are the same size, the same pixel there. And now what's that? B is a spatial representation obtained by IDFT of A. So you can see the sync function in spatial domain. This is frequency domain. What's the C? Result of passing zero twice the length of that continuum. So you tell me I'm going to do the Fourier transform frequency multiplication, but I'm going to have some passing zero process to make sure their boundary will be not wrapping around. The wrapping error will occur. So we passing zero here, right? Result passing zero to twice length of the B. Okay. So my original image sync function, I'm passing zero there. And what's that? D is a corresponding filter in the frequency domain obtained by the computing DFT of C. So this is the spatial domain. Zero padding. Right? I just remind you, you have to do zero padding of your original signal. And what's the result of this effect? When you padding zero there, they will have some ripple effect. Why? Because the discontinuity. Discontinuity, T-I-N-U-I-E-S, discontinuous, because you see the sync in a certain point, they stop in certain range and point, and you are going to pay zero there. But from mathematics, you know there's a discontinuity at a boundary point, and you are going to do Fourier transform. Okay, so this is the final Fourier transform. And you cannot expect there's an ideal low-pass filter there, unfortunately. Especially you have a boundary, discontinuous boundary in your time domain, spatial domain, and you will cause this effect. What's the effect? We call it ring effect at the boundary. Okay, so it's depending. What's the difference? What's the discontinuity difference? And cause some ring effect at the corner. It's not become ideal anymore. Okay, so in discrete Fourier transform also have this small effect at the ring, at the boundary. So that's the reason we will see. Some of the we will see later. Okay, I think it should be a next class, and you are going to apply some ideal low-pass filter. However, there are some ring effect will occur. I think it should be very soon, like this. Okay, this is the original image. Result filtering use the ideal low-pass filter, and see, is that ideal? Can you expect? What's that? At the boundary, there are some ring effect there. That's the reason the sync function at the boundary, there's some ring effect cause this result. Okay, so unfortunately, there's some ring effect there. Okay, even you claim it's ideal. Yeah, but unfortunately, the result will be some ring effect there. Okay, so it's causing ripple. It's also some wrapping around error there. Okay, so there's no idea. So let's see the real image application here. We use this IC circuit and the original image, an image obtained by multiply the phase angle by array by minus one. Multiply -1 in equation and the compute the IDFT. Okay, so now we have this image had a magnetic spectrum, and we change the phase. This is the phase times -1. So what's the result? Actually, no, -1 is the 180 degree. Okay, cosine sine. If you have a cosine theta plus 180, it's become -1. Okay, so some phase effect sine, it should be arctangent, or we call tangent. Okay, arctangent. So you become -1. So if you times -1, it becomes 180 shift. So it's a 180 reverse result, like here this one. So if your angle again must be careful. The positive, negative sign, and compute result of multiply the phase angle by 0.25. Okay, so if you try to change the scaling factor, -1 is 180 degree. Okay, you can expect. Okay, but unfortunately, if you multiply 0.25, what do you expect? You have to calculate what's the degree cosine 0.25 for the arctangent theta, and result like this. Nothing there. Okay, become disasters. So be careful. Again, the base angle is important. So we can I think we can summarize this class for this practical application here. Okay, I think the textbook write down step by step teach you how to do that one in a frequent domain. So the first, you have to know your fxy size. Okay, it's m by n, and you have to understand your hsy size of hsy. Hsy maybe I don't know, maybe some different size. Okay, so KL. But here, I think they try to pattern 0 to the PQ. So this is original m by n change to P to Q. Okay, and it's depend on your filter. And then multiply by, what do you do? It's multiply by -1 to x power of x plus y. So this one is a new image, okay? And spectrum of F. So this is new image spectrum. This is spectrum of, this is zero. Sorry, let me see. See result multiply FP by this one. Okay, so this is the multiply result multiplied by -1 to xy, and this is a spectrum. So you can see center spectrum, local, and they can repeat. They should repeat everywhere, but the size is P by Q, extended. And then what's the E image? Center Gaussian low-pass filter transfer function. So it's a Gaussian low-pass filter we just mentioned, and also it's a P by Q. Okay, it's an original K by L, but it's extended to P by Q, the same as your extended image. And the F is a spectrum of the product. So it's a multiply of this one, this F by H multiplication, pixel-wise, corresponding pixel multiplied together. And then G image is this is G image is the real part of the IDFT of this one multiplied by this one. So this I mentioned. You have to multiply this back. Okay, so this one, part of the IDFT of the HF, okay, multiplied by this one. So remember, do it again. So in a Fourier transform, the method I remember is called IFFT shift. Okay, you can shift it back and then extract n by n. This is your final result. Okay, so just to remind you, you are going to do this homework, and all the process cannot be skipped if you want to get the right result. Okay, yeah. So what's the low-pass filter here? We are going to do some Gaussian practice like this one. Okay, this is the final page. It's a curve, the curve, no? Okay, so I think the curve is round. Yeah, so we'll see this one, how you design the low-pass filter. As long as you have a Gaussian, and then you can do a lot of different combinations in time domain, spatial domain, and you will get very good result for your application. Okay, so we'll see it next class. Okay, time is finished.好，来。
为什么不可以用这样？所以我们
来，第三题是什么？来，题目是什么？
就是
第三题题目是什么？
那个 histogram
哦 ，histogram correlation。好。
我没有知道，我没有知道，到底这里是一个这个题目是什么？但是我听过问什么？
要什么
histogram 过来
但是我们取中位
这是标准。
你说你这样标准，我也要
不行，
这
个是 edge detection， 这不是这个这也不是对，
这个嘛，你看一个样子，
我看不一样，这结果一定不一样，结果一定不一样。
我说结果不一样
emphasize 对，这是 emphasize 高的image，那叫 edge enhancement。
他们那时候写了一块，
那 histogram 也要那是标准程序，你一定要知道这个标准。
对，一定要从那个就是它那个几率到几里面那个
几率，一定要几率来弄，因为我是在看几率，我要把几率变成 uniform 的几率。你这不是 uniform 的几率，所以它不是 equal， 它是 edge enhancement。原来你在问我这个问题。
那后面这个呢？
这个就怎么样？他是给你分，对不对？
对，来，
没有分啊，这题目问题。哦，
再讲我不行，还要。
那它有标准的 ，Canning 有标准的4个程序啊。
哦，所以那4个程序
那4个程序啊，不行，那2个就不叫 Canning 了。你把 Canning 丢到哪里去？哦，我是不知道这种到底怎么好。那你看那个，对啊，就是比较明显，你这个知道，它一定是怎么样？这个比较，对不对？那这边就是对，这边就是它会表示在平均，这样，可以吗？这个你知道，这个也是说比较长，然后这比较宽的，对啊，那个是这边比较宽，没有看到这个 sin 方形是标准。对，它那比较胖的是可能。对，
我们有没有说150好了？
对，那就是这样。它这个是比较宽。
下午没有空吗？下午我要先吃饭了。
它这边比较宽，
然后我可能
对，最先到我，然后
没有，我说原本是说礼拜5，可是那现在变掉了，今天。
对，那他对应的，礼拜5我有来。
那你那时候应该跟我讲，因为我给大家都不知道，因为我角度很奇怪，因为我们跟老师讲说我们有事，然后我们拿到读书啊，我们看到我们在
越有
那年都没跟我讲。
这个我看类似线，但是那有能量的地方，白是最在这个能量，它这个白是为什么不能？这条是最条线。这条，刚好垂直，我应该
说放一口袋子，老师说不行，不能用这个奇怪的老师。理工要从比较直接从这个开始，所以他都这样分，他都这样子。
对，这里来看，你就是把因为它垂直，所以它最明显是水平，最明显的那种。啊，那你说我要为什么这样？这个，它最明显是这一个。因为在哪边？这个它是因为它就像在那个，我不知道它有点正比多，能量它里面有一些，就相对于就那个这你同步的话，那你那个那这个水平会最低，因为它是垂直线。你要出来垂直化，对，它垂直化，它写这个有一条线，再看这个。这个有一条在这里，那它这个对。那你说这条是哪里？那因为很多的它有很多这个首先这条线，就是它很多打架，对，这种其实就是有两个垂直的线，它两个中间，但垂直也有，垂直也有该对啊，就是它要跟它这个两个直流线而言。就直流不见了，DC 是不是没有频率？对不对？频率欧米伽，换过来，欧米伽是频率，可以选择它这些频率，频率是什么？所以你在输入你可以选择频率是一个数字，频率还有很多不同频率的频率，然后频率是有频率的。 所以你今天给我们一个随便的信号说，啊，你不好意思，那很简单，
那你后来写吧，
那的这个题目，这个题目，这叫复习，也就是这个地方就你这样做出来呢，就是在复习。
你如果把2×2当做10套出来，
所以它是
我把出来，它就看这个大的这样子。
这样你现在这个信号的状态，那这个没有很难，这个出来，我一个影像过去题目，然后呢，在中间那点再讲你们，就是来有点是这样的。OK 啊，然后呢，越接近中间的话，是比较低。越接近中间的话，它高点在哪？最高点
就是跟这是一样。
高点这个里面来看，高点就我说的，还有问题再问，还有问题。哦，这个是标准数学，数学是推导题，数学推导题，你用连续或是离散就可以。它只是为了要让式子看起来简单，写成就好写。对，那把 n 升到那边去，结果是这样。结果是一样的，都可以，因为它是对称。好，你要把这个 n 跟 放到上面，放在下面，但是那个 n 跟 m 要一样，要一样的 size， 好吧 ？n 跟宽高不一样，才能够分开，式子变成一的，所以它有时和这个什么都有，所以跟它写一个式就好了。